Road freight moves almost all cargo in Colombia, but is also the major source of emission, especially Scope 3, which is large and poor managed. Most decarbonization effort fails because they assume all freight operations are the same. Our project used operation data for more than 100,000 real trips to identify distinctive freight profile and connect each one with the right decarbonization levers. Our question is, how can data help prioritize what actually reduce emission? Our hypothesis is that the target data-driven action outperform generic policies, delivering faster and more cost-effective results.
The core problem is that the industry in Colombia is structurally fragmented, and generic decarbonization initiatives fail because they don't account for this heterogeneity or the lack of consolidated operational data for Scope 3 emissions. To solve this, we developed a 5-step data-driven methodology using a massive data set of over 123,000 trips. We first performed rigorous data cleaning and variable transformation in Python to standardize metrics like load factor, vehicle age, and fuel type. The heart of our approach is the K-prototypes clustering algorithm. This unsupervised learning technique is unique because it allows us to analyze both numerical and categorical data simultaneously, uncovering patterns that traditional methods can miss. We didn't just create clusters, we validate the optimal number of clusters using the elbow method, the Davis-Baldwin index, and silhouette scores to ensure mathematical accuracy. We then applied some multiple linear regressions to each of the 4 resulting clusters. This allowed us to identify over 10 statistically significant variables per cluster, explaining up to 58% of the variability in Scope 3 emissions. And finally, in the 5th step, we mapped these statistical insights to a 5-lever framework. This methodology allowed us to move beyond a one-size-fits-all solution.
For the cluster 1, the model identifies fuel type as the primary penalty, with gasoline vehicles emitting substantially more than the baseline diesel. Recommended interventions for this cluster are linked to the vehicle utilization lever, like urban consolidation centers and collaborative logistics. Otherwise, Cluster 2 represents the backbone of Colombian logistics, comprising 100% of long-distance trips, and the regression highlights natural gas as the most transformative intervention with an efficiency coefficient of minus 1.05. Cluster 3 operates at a higher operational standard, with load factors predominantly exceeding 60%. The regression analysis provides evidence for a technological shift. Hybrid propulsion systems demonstrated that highest marginal potential for emissions reduction across the entire study. Cluster 4 achieves the lowest emissions intensity among urban segments. It utilizes heavy-duty vehicles with high load factors. The regression indicates that the 60 to 80% load factor range delivers the maximum efficiency. However, the model shows that older vehicles impose a significant penalty on efficiency. Therefore, recommendations focus on fleet renewal and fuel substitution for this cluster. This research establishes a reproducible methodology for data analysis and clustering, successfully revealing the operational archetypes that define Colombia's logistics landscape. Our statistical evidence highlights specific levers for decarbonization. This research establishes a reproducible methodology for data analysis and clustering, successfully revealing the operational archetypes that define Colombia's logistics landscape. Our statistical evidence highlights specific levers for decarbonization, demonstrating that vehicle technology is the primary driver of urban efficiency, while load factor and fuel are critical for long-haul performance.